Hello, everyone. My name is Dobroslawa Kwiatkowska, and I am very honored today to speak with Professor Gerald Pollack again. Hello, Jerry.
Hello, Dobrosława. It's so nice to see you and to be with you. I'm really looking forward.
It's actually, first of all, for me to say that we are deeply, deeply honored that you accepted our invitation to be a speaker at our third international conference for energy and information medicine in Poznań. Thank you so much.
Oh, I'm thrilled and delighted. The last time I was there, it was really an eye-opener. So looking
I remember, yes, I remember that you were very inspired. You told me you loved Poznań and the atmosphere, which was there in the conference. What do you remember most from the conference?
Well, I remember, of course, the interesting presentations, but also the friendly atmosphere. I go to many conferences and meetings, and we try as much as possible to make our water conference in the same vein where people get to know each other, and it's very friendly and open. And your conference, I felt, was exactly the same. So I think you aspire to the same, and you succeeded in making it the same. And therefore, it's one of the reasons why I love to come. So thank you.
I'm happy to hear this. I'm really happy to hear this. As a president of this association, first of all, I would like also to thank you that you actually said yes to join to our advisory board. For us, it's very important as an association to have you. There is a Dr. Hendrik Treugut, who you know. There is Beatrice Milbert, who you know as well. So we are very happy to have you in our advisory board too. Thank you so much.
Well, I'm happy to be there as well. Whatever advice I can offer. I'm not sure how useful is my advice, but I try.
Oh, please. You heard from me many times how fascinated I am with easy water.
Yes, I've heard.
The short state of water, and with your work. In my eyes, the easy water and all around it, your books, all the accomplishment of yours, is a huge gift for science. It's a huge gift for humanity as well, because the more we get to know the nature of easy water, the more we actually are able to comprehend the nature of living beings, of ourselves. However, I asked myself a question, what we still don't know about easy water. And when I was preparing questions for you, I was thinking, I will not ask you about easy water in general, because we've had this conversation 2 years ago already. And I think you are asked all the time about the same, very often. But I would like to know what we already are sure about easy water, I mean, and where are open questions without clear answers.
Okay. Let me respond to that. First of all, what we know about easy water, and if I wander off too far, please remind me the second half of the question, what we don't know, because I think that's clear. So what do we know? Well, so we know that water, ordinary liquid water, undergoes a transition it undergoes a transition from liquid water to easy water. And that transition occurs under a couple of circumstances. One is that it needs to be next to a hydrophilic or water-loving surface. And if it does, and if it has the right energy, I'll tell you about the nature of that energy in a moment, it undergoes a massive transformation. And the transformation is to typically negatively charged entity, which is actually H3O2. It's not H2O anymore. H2O is neutral. And so if it's negatively charged, it can't be H2O. It's H3O2. And if you actually look at the structure of it, it's a planar structure which builds right next to the hydrophilic surface. And that planar structure then nucleates the growth of the next layer, which is also a similar planar structure, which nucleates the growth of the next layer, and so on. And these layers can grow up to hundreds of thousands of layers. It's really massive. It's not trivial. When we found that the exclusion zone, or EZ, or we say fourth phase water, because that water is so completely different from any of the three phases that we know. So we call it fourth phase. Sometimes we say EZ for exclusion zone, or fourth phase. Yeah. Now, if that's negatively charged, if you think about it, we start with neutral EZ water. And if we see a zone, a big zone, that's negatively charged, somewhere else there must be a zone that's positively charged because, it's like 1 + 1 = 2, or +1 + -1 = 0. Maybe that's a more apt description. And we found it, and exists just beyond the exclusion zone. So you have a hydrophilic surface, and then next to the hydrophilic surface is the fourth phase water, or EZ water, negatively charged typically. And beyond that are protons, or actually not really protons, because protons, positive charge, they latch onto water molecules. And when they latch on, they're called hydronium ions. It's really like positively charged water. So you got negative charge, exclusion zone, positively charged water. Negative, positive is a battery.
Sure.
And batteries supply energy. And we demonstrated not only the centrality of EZ water, because it fills the cell, the centrality of that for cell behavior, but also the energy source. This energy exists in your cells. And the question is, well, if it exists in your cells, is it actually used? And it would be surprising if there's an energy source and Mother Nature decides that, well, we're not going to use it, we'll just let it sit there. And we already demonstrated that it's used in the cardiovascular system, and also in many different cells. So, and recently I've been looking about the energy. Everybody thinks that the energy comes from ATP, from the high energy phosphate. And I've been looking at the evidence, and to my surprise, this finding came from a guy named Lippmann in 1941. Everybody was thrilled because finally, everybody could understand that the energy source was right there in a molecule that's all over the place. And I found 3 publications, and there's a 4th one that I'm looking for now, that challenged that point of view. And in one of the papers, an extensive report by Morales and Podolsky, 2 people who I know because they're in the former muscle field, prominent investigators. I mean, the field I used to be in, and they looked at the energy that could be supplied by the high energy phosphates of ATP, and they could find nothing, no high energy phosphate at all. So this raises the question, and that's unanswered. It's one of the unanswered questions. There are now 2 options for energy sources. There may be more, One of them is ATP, but that has been seriously challenged. Few people pay attention to the challenge because, you know, I guess maybe habit, or you believe what everybody else believes or whatever. But I think that issue absolutely needs to be addressed. And if it's not the high energy phosphate bond from ATP, it could be the electrical energy that we've been talking about. You know, it's not resolved. I think there are two sides to the issue. It needs to be resolved. Just one more point in what's kind of known, and that is the energy. You know, you have to charge a battery. If you leave your cell phone, forget to plug it in overnight, the next day it won't be working. It needs to be charged. Its battery needs charging.
Yeah.
And the same thing is true. Same thing is true of this battery. It needs charging, and we found, I should say, not we found, well, maybe we is accurate. It was a student in the lab, a young undergraduate student, who one day was working with a chamber, and one day noticed a lamp sitting next to him, and he grabbed the lamp. It was one of these gooseneck lamps that you could bend in every which way, and he shined it on the chamber, and the region where that received the illumination, the EZ exclusion zone, grew enormously. And so he called me in, and I took a look at it, and of course we did many experiments after it to confirm and deduce which particular wavelengths of the lamp's spectrum is really responsible. And it turned out that by far that the most responsible wavelength was in the infrared region, which we usually associate with heat. Infrared light, feeble amounts of infrared light could build the exclusion zone by 10 times. It's really, really powerful. So the charging comes from infrared energy, which is all over the environment. You know, many people think, oh, it comes from the sun because we feel the heat of the sun, and we think, oh, that infrared radiation. But in fact, it's just all over the place, because if you were to turn off the lights where you are, and even your cell phone camera couldn't pick up an image, an infrared camera, which is just like any other camera, but the sensor is sensitive to the infrared wavelengths instead of the visible wavelengths. Pick up a beautiful image of the picture that's behind you, of the stripes on your dress, et cetera, everything. And that's why the military uses it at night to check out the enemy tanks and rifles and what have you. So the energy is always available, which means, or at least some energy is always available, which means that the energy required to build easy water is available, which means your body is full of easy water.
Yes.
So that's known. Also what's known is that easy water fills your cell. And that, I've argued in various venues, is what's responsible for the negative charge of the cell. It has nothing to do with pumps or channels. You know, I could go into the various arguments here, but I'm sure there are more important or more relevant things to talk about. But the important point is, I believe we know. Other people may argue that the reason the cell has a net negative charge is because it's filled with water, easy water, that has a net negative charge. So that's what we know. There's a lot more. You know, I could go on and on, but okay, here's what we don't know. One of the things we don't know, there's actually a lot we don't know, but something that I think is relevant for your particular interests. You know, it has to do with information stored in water, or memory of water, or such, and how information can be stored in water. Some time ago, it was considered preposterous that any such thing could happen, because we mostly thought of water, of this kind of water, liquid water.
Mm-hmm.
And in liquid water, the molecules are not only randomly oriented, but they're bouncing around a fierce number of times per second.
Yes.
Or per millisecond, microsecond, femtosecond, whatever. And it's kind of hard to think of how information could be stored.
Mm-hmm.
But on the other hand, the discovery of fourth phase water offered an opportunity because remember, as I mentioned, this is a sheet-like form that builds multiple sheets, but each sheet, if you look at the structure of each sheet, it's a regular honeycomb sheet, and that is the oxygens and hydrogens are arranged in hexagonal fashion. And
exactly.
you know, there are many structures that are hexagonal. This is not unusual, and this is one of those structures, and I think an important one. And so, since there is a lot of information now that is demonstrated objectively that there is such a thing as water memory or information stored in water, you need to figure out a mechanism. So we started looking into this, thinking that, well, you know, maybe EZ water is the substrate in which energy or information can be stored. And to do that, we compared the structure of an EZ sheet. There are many sheets, but just one sheet to a computer memory. So if you consider the thumb drive, you know, that you stick into your computer to store information, how does it work? Well, it works because it's a two-dimensional array of transistors. Each one is at a fixed point in a rectangular grid. And each transistor of the numerous transistors, each one can have two states. One is an on state, one is an off state, or a zero state, one state, anyway you want to look at it. And it's the distribution of these zeros and ones throughout that large array that is responsible for the memory. So what the criterion for something to store information, if we base it on what we know stores information, it has to be a regular array of some sort, and it needs to have an element that can have different states. So now think about the EZ and EZ water. It's a regular array because it's hexagonal. It's not rectilinear,
yes.
But it doesn't matter. And it's got oxygens and hydrogens. I think as far as I know, the hydrogen is nothing really particularly interesting, but oxygens, yes. And the oxygens, in fact, can occupy 5 different states, not just 2, but 5. And -2 is what we learn mostly in school. We call it valence. But actually, it's a so-called oxidation state. And there are 5 oxidation states, which you find in any mid-level chemistry book. And so it's -2, -1, 0, +1, +2. So it means that in the particular EZ array or fourth phase array, one of the 2 entities can have 5 different states. So the 2 conditions are satisfied. The regularity and also the fact that one of the 2 elements can have different states. So in theory now, from this, at least in theory, this is a reasonable substrate to store information. And we know from so many experiments that information is stored. And I think this is the way that PEMF or FSM could work, because if the particular frequencies are impacting the oxygen, any one or number of oxygens to be in one state and another state, then you have an opportunity to store this kind of information, and it could make a difference in the EZ that grows. So when I was alluding to unknowns, there are lots of unknowns associated with this because nobody knows exactly how to put the information in and get the information out. And this is the frontier. And for me, it's really one of the important frontiers. Another frontier, of course, is to figure out the extent to which the EZ or fourth phase energy is used in biology. And I think it's extreme, but it's still not known. So those are, and I'm sorry for the long answer to your short question, but those are, you might say, some of the unknowns.
The question was so constructed to provoke a long answer, actually.
Okay, well,
I'm happy with your long answer. And you know, as far as I know you, you are this type of a scientist who has a huge respect towards unknown. And you are not afraid to ask questions. And one has to have a courage to ask questions, because when we ask questions, we actually are forced to face the unknown, and it's not always comfortable. Yes.
Well, thank you for the accolades. You know, it reminded me. Somebody else asked me about that, and I think my proclivity to search for truth, which is really what you're alluding to, it actually came from a psychiatrist. I was in the middle of a difficult marriage, and my ex-wife, this is long ago, she had some issues with alcohol. She had issues, psychiatric issues, borderline problem. And this psychiatrist was wonderful. And one of the things that he said over and over and over again is, what you really need to do is to penetrate toward the plain, simple truth, the plain, simple truth. He had an enormous impact on me. And I guess maybe that was a turning point, or one of the turning points in my life. I think that there had been a natural proclivity to try to find answers, which is really the same as to find truth. But I learned so much from that guy, and I think he had such an impact. And so now, essentially, what we're doing, and pretty much all we're doing, is trying to penetrate toward the plain, simple truth. And I guess this is late enough in my career that I'm not fearful of getting thrown off or thrown out, because you know, we've produced quite a lot, and there are actually a few books that are in various stages of completion, which do exactly that, penetrate toward what I believe is ground truth. You know, and if everything stops, it's okay. You know, if I get the Ig Nobel Prize, maybe you know that prize is given by Harvard University students to improbable research. And it was the latest person I know who got it was Jacques Benveniste, who
we love Jacques. And we love Jacques.
Yeah, he was my friend, and he, unfortunately, he died prematurely, and he was despondent because his career was basically terminated, and in a grossly unfair way. And his results on water memory have now been confirmed by others, and so by multiple others. And at the water conference, as you know, he's a hero for his memories.
And he was courageous as well. You know, I think maybe that's why, I mean, maybe because I know that you have this courage and that you are open to questions. I'm not afraid to come to your water conference and present my hypothesis about the possible creation of easy water by microcurrent frequencies. I will ask questions, a lot of questions, because there are no answers yet. But I think it's the only way for us all, for the humanity to move forward when we are not afraid to ask these questions.
Well, absolutely. And I know you're in that realm also, asking fundamental questions, asking
Yes.
how.
Yes,
You have great
exactly.
curiosity.
And you mentioned your water conference. Of course, I would like to use this occasion that we are talking now and to invite all YouTube people, let's say, the YouTube audience to your water conference this year, which will be in October in Lisbon. I love these conferences, these events. Actually, each time when I attended your water conferences, it was a huge inspiration for me, and I met so many people, open-minded people, who until now are not only my inspiration, scientific inspiration, but also my friends.
Yeah.
You are. Uh, Please tell us something more about the water conference this year, because I think people who will be watching us would like also to know something more about this.
Well, the best way to find out is not from me. The best way is to check on the website because all the information is there, including a preliminary agenda. And I'll mention the URL. It's waterconf, water, CONF, just one long word, CONF for conference, but waterconf.org, not .com.org. And there you can find all the information. And a very nice website designed by my son, who's an artist. So I'm proud of him. There's a diversity of speakers in so many areas that it's really it's difficult for me to single out one of 33 or 34 as being, you know, perhaps the most interesting. I guess I would cite the diversity of speakers. Speaking about areas ranging, a lot of speakers talking about health and various kinds of energies that are used, like sound energies, for example. There are a few people speaking about that.
Yes.
Electrical energies on health. There's someone speaking about primary water, you know, water, vast amounts of water that exist well beneath the surface of the earth.
Mm-hmm.
That's another area. Of course, information, memory, water is on the agenda as it is typically.
Mm-hmm.
And I'm going to be talking about the structure of the atom. And
I saw it. Yes, I saw it already, and I remember our conversation while we had been flying to Tuscany 2 years ago. And you mentioned already 2022 about your hypothesis. So I can't wait to see your lecture about actually atom from the other side, atom as we don't know it yet.
Well, yeah, so yes, that's exactly right. And you know, we have a structure of the atom. It looks like the solar system with a nucleus and the electrons circling around in different orbitals. And that's been around for let's see, more than 100, more than 100 years. I think it was around 1910 or something like this. By Niels Bohr, and you know, once it was accepted by the physicists, not the chemists. The chemists objected to it. They said this doesn't explain the simplest of chemical reactions. Therefore, it's a non-starter. But the chemists had their heyday in the 19th century, and this was the 20th century. It was the day of physics. It was the era of physics. You know, all the Nobel Prizes given out every year by another physicist who discovered another subatomic particle. I think the number now is more than 60 or so. And one subtle problem, this is not the main problem that I bring up with this structure, but a subtle problem is when you have a theory, the sign of a good theory is that it explains not only what you're intending for it to explain, but progressively more things that you hadn't even thought of fit right into the theory. It's the sign of a good theory. The sign of a bad theory is you have to keep patching it to make it work. You know, it doesn't quite work, and therefore you add something and add something else. And so I would cite a book by a guy named Unziker, who I've almost finished reading one of his books, and I'm profoundly impressed because he talks about what happens. You know, so we have the solar system model, and to make it work, because it doesn't work for a particular experiment, you add a subatomic particle, and then you do another experiment and it doesn't work. And so you add another subatomic particle to make it work. And then another experiment still doesn't work, and you add another subatomic particle. And this is basically his point. And, you know, it's easy to agree with a point like that, but the major issues that I raise in the book are different. There are instabilities associated with the model. So, for example, the nucleus is positive, the electrons are negative. And so, you know, we learned in school that negative and positive attract one another. And so the question is, how come those electrons don't collapse onto the nucleus? And if they do collapse onto the nucleus, then the atom collapses from taking up space, which it must do, to zero, to nothing, to a point. So it's unstable. That's just one of a half dozen different issues that plague the model. So, you know, what you can do is, and what has been done is the model has been amended in various ways with the addition of quantum mechanical subatomic particles. But there reaches a point where, you know, if the model is unstable, it can't be correct. And therefore, for that reason I mentioned, plus other reasons, which I won't bore you with, the model simply doesn't
You
work.
never bore me, you know. You never bore me. We could sit here, you know, we could sit here for 5 hours and I could listen to you. I know only I am responsible for keeping the space and time, but you know, these courageous steps you are making, it's something what we need nowadays. We need to go outside the box in many areas, and not only in the water science, but in other areas too. And when you say, okay, from my point of view, and you are a very experienced scientist, this model is not stable at all, there is space to investigate it. Sure.
Well, thank you for the accolades, and I appreciate that very, very much. And it's true, you know, and it's natural, you know, we're as humans, we have a natural inclination to find out what's true and what's to find out about nature. How does it work? Unfortunately, the system of doing science now doesn't really allow you to do that, because if you have a revolutionary point of view, and you want to get some money to study it, because you have to hire some people, and hiring costs money, and you're more or less obliged to apply for grants. And what happens is, if you apply for a grant, let's say I love this particular analogy. Let's say, you know, you think the Earth is round or spherical, but everybody else thinks it's flat. I can look out from my home where I am now, and I can see Lake Washington. It looks flat to me. So, you know, it's easy to think that the Earth is flat, but you come upon evidence that maybe the Earth is round. You've seen some images taken from space, and you could see the curvature. So you take that as so-called preliminary data, and you apply and say, hey, I have preliminary data, and that it looks like, despite the fact that everybody knows that the Earth is flat, I think it may be round. And this is really important. So your application is received by a gatekeeper, either the National Science Foundation, or I don't know what the European equivalent is, or the Polish equivalent is, but and the gatekeeper says, "Oh, you know, I don't know this person, but what she's proposing, it looks pretty profound, and if she's right, it's really important. If she's wrong, well, I'm not sure. So I'd better do my job conscientiously and hire the best reviewers in the world." And those are the flat Earth people, the most prominent people in flat Earth. So your application is challenging those people. You know, it's like the French revolutionaries going before Louis XVI and saying, you know, we have a few bones to pick, and you know, how far are they going to get? So this is the problem, that if you have a revolutionary idea, you'll be judged by the person or people you're challenging. And you know, any scientist with a sense of reality, if they want to get money to fund their lab and to put food on the table of the people working in the lab, they better toe the line, which means they better not veer off from what's accepted. Otherwise, they're going to run into problems. So this is I mean, the entire system, the whole world system, practically every funding agency works on this principle, which means there's aren't going to be a whole lot of revolutions. And there haven't been. If you ask yourself, how many revolutions, how many genuine important scientific revolutions have occurred in your lifetime, say, that's about 29 years or something like that.
You are so cute, Jerry.
Okay, 33.
Yeah, almost 50, if you want to know the truth, my dear. So
I was
there have
joking.
been few, there have been few
Well,
revolutions, but not many.
not many, yeah, not
No.
many. And some of the so-called revolutions, and I'm talking about not technological revolutions, but genuine science revolutions, that
Yes.
something that changed our life, like the genetic code that was the mid-1950s. And a lot of what you might call revolutions are built on that, but they're really not revolutions. They're extensions of the revolution. And you know, the splitting of the atom, of the nucleus, to get nuclear energy and so on. You know, those are real scientific revolutions. And you mentioned that you know a few. Many other people have said, "Oh, you know, I can't think of any," but there aren't many for sure, and we need them, because scientific revolutions inevitably wind up provoking technological revolutions, and these technological revolutions are seriously needed to solve our world's problems. And sometimes the technological revolutions are something that you never could have imagined before the scientific revolution occurred. Example, Bell Labs, early in the 1900s, some scientists were playing around and they found they discovered semiconduction. Now, they could never realize that semiconduction would result in AI and with your laptop and cell phone and such. It took some years, but that was a revolution that occurred, which spawned huge technologies that govern our life right now. And those are kind of examples of how scientific revolutions, if they actually could occur, might have the capacity to solve some of our problems. I particularly think about water, because you know, water is one of our problems.
Yes, but
going into.
I think
I'm sorry, the sound.
there was some interruption. Maybe the Wi-Fi was not stable. I think we need also courage to come back to nature, because it's a lot of technology around us, and we are at the point that we have to remind us every day that we are part of the nature. And I think that water in us has the capacity to remind us about it as well. That we keep the balance between the technological and scientific development and being deeply rooted in nature, because it's our home, it's our source, it's our everything.
I couldn't disagree with a word you said. Absolutely.
Yes.
Really important.
And back at the end, back to my conference for energy and information medicine in Poznań. You know, I'm very happy that I was able to help you with publishing of your book in Polish. I mean, to contact the publishing house, COS, because for me it was like, you know, something of the heart. I miss now the word, but just a part of the heart. I read your book in English, I read your book in German, and I was dreaming to one day read, to be able to read your book in Polish. So I'm very happy that your book will be there soon, to amaze our Polish readers as well. As you know, I invited the COS Publishing House, that they are a part of our international conference. And I hope that they will make it to organize the premiere of your book in Polish. It would be wonderful.
That would be fantastic. Yeah.
That would be absolutely fantastic. My last question, almost last, I have two left. My question is about the book. What would you wish for the Polish reader who will open your book, Fourth Face of Water?
Well, I guess what I would wish is the same as for others who read it in their native languages. There have been quite a few translations, and one of the last ones someone is working on in Spanish. It hasn't been that way, but you know what I would hope is that it opens their eyes, and I think a lot of people are. I'm finding are really eager to find truth in nature.
Mm-hmm.
And the book is presented in attempted to be presented in an accessible way. So this is not intended for people who have been in scientific careers for 30 years. They're intended for people who maybe they've had one course in chemistry or one course in physics or something, nothing more. It's presented, or there's an attempt to present it in ways that are clear and understandable. And I think that's important in any kind of scientific presentation. Many of my colleagues disagree. Some of them
absolutely
stand up. You know that. So they'll stand up and present something that's so complicated that even the experts are having trouble. And the implicit message is, my subject is very complicated, you know, and look how smart I am because I know about it, but I'm sorry that you people can't understand it. And that's the antithesis of what I think nature is all about, because I part of my belief system is Mother Nature works in simple ways. You know, the principle of Occam's razor. You've got two hypotheses, competing hypotheses, and the one that's simplest is the one that's likely to be correct. So I believe Mother Nature operates with simplicity, and anything that looks complicated, I smell problems.
Is suspected.
Suspected. And so I hope the Polish readers, and you know, I understand that not everybody speaks English.
Yeah.
I guess I'm lucky to be in that realm where it's easy for me to read scientific literature, but I understand. And the book is meant not for scientists. It's meant for anybody who would like to find out about water. And I hope that is true of the Polish people as well. I'm sure it is.
Mm-hmm.
So,
But I think that scientists will be inspired as well, Jerry. The book is very multidimensional, I would say, and also scientists will have their, let's say, party for their minds. I mean, party in the sense that there will be something fascinated, what will inspire them to maybe what will wake them up. It's a great book to wake also scientists up, I would say.
well, thank you. You know, that's part of the hope. The book, you know, if you flip through it, it looks kind of light because there are cartoons in it and many illustrations done by my son, who's a talented, actually a sculptor. And one day he said, "Dad, I want to illustrate your books." So, um, yeah, and so many people have commented on the illustrations because the illustrations, my son really understands the material that's being illustrated, and he is so talented with uh, not only illustrating, uh, 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 not only with illustrations that are designed to illustrate the point, but with some cartoons also, some humor. And
Mhm.
I hope the humor is appreciated. I know the Polish people are full of humor, so um,
Oh, yes.
that should bode for acceptance of the Polish translation.
I'm
And I
sure
know
yes.
the editor of the oh, just to say the editor is a former student of mine, and she knows the subject very well. So if she's editing, I'm sure the translation is a very good one.
I'm sure everybody will love it. That's something I'm very sure about, and there are not many things we can be sure about in life,
Yes, isn't that
isn't
true?
it? Last question, Jerry. Is there any question about your work that nobody has asked you in the interview, although you would like to answer it because the answer is absolutely fantastic?
Oh my goodness! Wow, that's a question I never received.
I was hoping, yes.
That's a very original question. Boy.
Because, you know, I was thinking that sometimes we carry in us something we would like to share with the world, but nobody asked us about it.
Okay, well, so one of those areas is homeopathy. Um,
Okay.
um, you know, homeopathy depends on. I've been asked about homeopathy. I don't think ever, or maybe once or twice. And I participate in a lot of interviews. So,
Yes.
and you know, the question is, well, when you do all those dilutions, uh, how to, how is it possible when you've diluted beyond the point where where any molecules of the original mother tincture, let's say, should be absent? How can the information penetrate? And I've been thinking ever since I heard of the fantastic studies of Alexander Konovalov,
Mhm.
um, whose work he passed recently. His work was presented by Vladimir Bykov
Yes.
uh, at one of the conferences, and I think he did more work on high dilutions than anybody in the world ever. And and he was a prominent guy. He was uh, he became the director of large, famous chemical institute in Kazan in Russia. And then he became the rector of his university, University of Kazan, which is ranked very high in Russia, just below Moscow and St. Petersburg. So this is a man of great distinction. And at the end of his career, or toward the end of his career, he spent his time studying what happens with high dilutions. And I wanted to communicate with him about my idea, a simple idea about the information transfer, but I never got an opportunity. Unfortunately, he passed. So let me just tell you a very, very simple idea about the information.
Please do.
Yeah, so when you start with original mother tincture or some substance, some natural substance, what happens is that easy water grows next to it. So easy water grows, and the issue with easy water is rather fragile. So we found in our experiments, or in between our experiments, that if you take a chamber with easy and you pick it up and kind of move it a little bit, the easy would break up, and it breaks up into little easies that when you put the chamber back down again, they reassemble. And so I'm thinking that Konovala found that the succussion, that the shaking, is an absolutely necessary condition. And if you don't do it, it doesn't work at all. So I know what happens when you shake it, the easy breaks up into a lot of little easies. And so when you do the dilution, those little easies, a fraction of them will be in the dilution. And you can do these dilutions on, practically infinitely, and still there should be some of these. So this is a question that nobody ever asked me, and I haven't thought through in enough detail to know whether this is a legitimate hypothesis or not, but I bet it is. And if I have the time, I want to pursue it. So thank you.
So I'm happy that there was such a question. Thank you so much, Jerry, for this lovely and inspiring conversation. I enjoyed it as always. Allow me only to share the screen so I can show our audience where they can buy the tickets.
Okay.
Because as you know, sometimes when we are talking about an event, it's not easy for people then to follow where then can buy tickets to a conference. Here we are. This is a website, Evenea, as you can see above. And here you can buy our tickets. I will place the link to the website. And when we scroll it down, we can find also the English description about the conference and about the speakers. And also we can find program here. So it's one thing. And the second is our Facebook profile. I mean, the Facebook profile of the Polish Association for Energy and Information Medicine. Please let me to share it. Here we are. So everyone who would like to attend our conference, who would like to be a part of our association, to be a member, can visit us here and on Facebook, or also www.ptmiai.pl. I will write everything down under our interview. Thank you, Jerry.
My great pleasure.
Can't wait to hear your lecture, and I wish you a good time in summer.
Okay. Thank you very much. Okay.
Bye-bye.
Bye. So
I will